So now we are going to discuss about the work energy principle. So work energy principle. So you have already seen from the note that this particular relationship or this principle states that the work done, which is force times distance, is equal to the change in kinetic energy. Okay, that is delta kinetic energy, change in kinetic energy. For change in kinetic energy, we know that kinetic energy is given by half mv square. So when we are talking about change, so it's going to be half mv square minus half mu square, where v is the final velocity and u is the initial velocity. So this expression can be written as half m into v square minus u square, which forms our expression for work energy principle. So these problems are also from the kinematics, because the object is moving, so automatically the equations of motions comes into the picture rather than the static condition. So for objects in motion, we have already seen the D'Alembert's principle, which basically states that sigma fi is equal to mai. That is the D'Alembert's principle, and this is another principle derived for objects in motion. A very simple example to demonstrate how we can use this particular equation for solving problem. Okay, let's consider we are having a pulley arrangement. Okay, a pulley arrangement like this. So I am having a pulley. Okay, and there is a block. Okay, a block having say mass 50 kg. Okay, and I'm applying a force in this direction. Okay, a force in this direction, say 1000 Newton. Now I want to see, or I want to calculate the amount this block will be moving after some time, or maybe the velocity of the block or acceleration of the block. Different parameters, these kinematic parameters of different, like the acceleration, velocity, distance travel, all those things need to be calculated. So from this we can from the basic principle of a pulley, we know that if it is a frictionless pulley, if this value is 1000, the tension here will also be 1000. So now what I'm trying is, I'm attempting to plot the free body diagram of this particular block. So when I plot the free body diagram, okay, the free body diagram will look something like this. So 50 G will be acting downwards, and there's going to be 1000 Newton acting upward, and as this force is pulling it upward, the acceleration of the block will be in the upward direction. Okay, so let's calculate the acceleration value. So to calculate the acceleration value, we can use the D'Alembert's principle that we already know. So I'm trying to do that. So I'm considering this as the I direction and assuming this as the positive direction. I can write the net force is 1000 upward and 50 G. So 50 into 9.81, that is downward, hence it is negative, is equal to mass of the object, which is 50 times A. From this, I can calculate the acceleration for the block. So the acceleration will be 1000 minus 50 into 9.81 divided by 50, which is going to be 1000 minus 9.81 divided by 50. I'm going to get a value 10.19 meter per second square. Okay, now I'm considering a different case here. So let this block moved by an amount 1 meter. Okay, this block moved by an amount 1 meter, and I want to know At the instant when this block is reaching a height of 1 meter, what will be the velocity of the block? Okay, now the block is moving. Currently it is in a state of rest. Okay, and when I applied 1000 Newton, it started to move. I applied this 1000 Newton consistently so that the block is moving upward with a constant acceleration 10.19 meter per second square. And I want to know what is the velocity of this block when it reached a height of 1 meter. Okay, so we have the equations of motion, the different equations we already have. So these are the basic equations we have. S equal to ut plus half at square, v square equal to u square plus 2as, okay, and v equal to u plus at, the different equations we have. Now let's try what our need is. Okay, this is u square. What our need is, I want to calculate the v at this particular point. Okay, so the best equation what I can use here is this particular condition, because what I know is I have the value of u, which is 0 because the block is at rest, and the acceleration I already calculated. The distance traveled s is known, so using this equation I can calculate v square. So I'm trying to substitute that. So I will be getting v square equal to 0 square plus 2 into 10.19 into distance is 1. So I'm going to get v as root of 2 into 10.19, which will be equal to, let's calculate it, 10.19. I'm going to get the value as 4.51 meter per second. So this is one way of solving this particular condition. I want to calculate v and I can calculate it like this. The same can be handled using our work energy principle. Okay, so I'm telling about alternate way. There is in the very beginning itself I said there is no one way of solving a problem. There are many ways. So this is the one basic approach that we have already learned. Now we are going to try with the work energy principle. Okay, so work energy principle says that force times distance equal to half m into v square minus u square. I'm directly substituting that condition. So I want to get the force. Okay, the displacement is in this direction, so force in that direction need to be calculated. So force in that direction is 1000 upward, 50 g downward. So net force is 1000 minus 50 into 9.81 in the direction of the displacement. Okay, and the displacement we know it is 1 meter. So this is basically the work done. And on the right hand side what I'm having is half times the mass of the object, which is 50 kg, into v square, which is the unknown parameter. U is available, which is 0. So directly I can substitute here the value of v square is going to be 1000 minus 50 into 9.81 divided by half into 50. When I do this calculation, I am again going to get the value of v as 4.51 meter per second. So this is the work energy principle way of solving this same problem, and this is the D'Alembert's method of solving it. So here first we are calculating the acceleration and then we are calculating the velocity. But if the acceleration is not asked in the problem, then there is no need for us to go through this way. Directly we can use the given condition. So it's according to the need we need to approach whether we require D'Alembert's principle or work energy principle. If acceleration need to be calculated, the best option is D'Alembert's. If it talks about velocity, the easier option is to use the work energy principle. So we can see a few more problems regarding this usage of work energy principle so that you will get very familiarized with this approach of applying work energy principle.